along this professional course program, you learned a lot about many different aspects of energy and indoor climate systems in buildings. In this lecture, we will recap and address how these different parts can be articulated into a design process that leads to energy efficiency and a healthy and comfortable indoor environment. Welcome to this lecture. In the first course, you learned about how to estimate the hourly loads for space heating and cooling, on which the determination of the nominal loads and the annual energy demand are based. You learned how to play with the building characteristics like insulation and type and size of glazing in order to decrease both nominal loads and energy demand. Let's look with a 2 floors detached house of 10 by 7 meter with a total floor area of 140 square meter, what its design may mean. I will show it on 2 examples of a similar house, the one being located in the Netherlands, it could look like the picture on the left, and the other one being located in India, in the region of Mumbai. It could look like the one on the right. Both houses have 35% windows on all facades, and the Indian house has also solar blinds. In the Dutch house, the indoor temperature is controlled between 20 and 24 degrees Celsius, while in the Indian one it is controlled between 22 and 26 degrees Celsius. In this example, I don't look at humidity. You see here the load duration curves for heating and cooling over 1 year. On the left, for a poorly insulated version of the house, that would be typical for the whole building stock built before 1970. In the middle, for a house insulated to current standards, which is a highly insulated roof with RC value of 6 square meter Kelvin per watt, and good insulation of walls and floor, around 4. On the right, it is for an extremely well-insulated house, according to passive house standards. RC value is around 8. Solar blinds were installed on the south facade, and there is ventilation with heat recovery. The scale is identical on all graphics, so you see here how important the physical design of the house is. You can make the most fantastic HVAC design on the poorly insulated house using, for instance, a heat pump of 6 kW and a gas boiler of 12. The point is that the energy usage will still be much higher than it could have been if you had insulated the house. You also see that the number of hours where heating is needed decreases with insulation. As for the cooling, in moderate climates, we often neglect it in old houses. There is a high peak, but it is only for a few hours per year. You see that when insulating the house to current standards, the nominal cooling load decreases a lot, but the annual cooling demand, the area under the curve, increases. The number of hours where cooling is needed increases. That's because a considerable part of the cooling demand happens while the outdoor temperature is still quite low, and well-insulated houses can therefore not lose the heat they gain by solar radiation. This would be even worse in passive houses, that's why solar blinds must be installed. With solar blinds in the passive house, you see that the cooling demand has decreased. For the house located in Mumbai, the heating demand is not very relevant, while for the cooling demand, you see here too the high influence of building design, and especially insulation. In all 3 cases, there are solar blinds. However, the decrease in number of cooling hours is not that high, that is because it is continuously warm. When the house is better insulated, the nominal power and the annual cooling energy demand decrease a lot. But this decrease is relatively less than for the heating in the Dutch house. This is because cooling is determined for a considerable part by solar radiation, which is not affected by insulation, while solar radiation does not play a big role during the Dutch heating season. Well, the message here is that a good HVAC design on a poor building thermal design is just like baking a pie with the most modern oven while using the wrong ingredients, salt instead of sugar, for instance. Also note that the physical design of the building is generally not a task of the HVAC engineer, but more the one of architects, structural engineers and building physics engineers. However, the HVAC engineer will generally be involved in making load calculations and advising on measures to be taken. In the second course, you've learned about energy supply and how the choice for the supply impacts the depletion of fossil fuels or biomass and in which CO2 and other harmful emissions it results. You see on the left a coal power plant producing enormous amounts of CO2 and particulate matter, while the geothermal plant on the right has none of them. The message here is that even if you design the most efficient HVAC system with well-thought zones and ducts and buffers and readjustments, if you have chosen an energy conversion system based on fossil fuels, that will not help a lot. A main task of the HVAC engineer is to help the client to choose suitable energy conversion systems and to guide on the financial aspects. The financial aspects are not only about investment costs, but also about operational costs, the energy bills. In future, it could also be about whole life cycle costs, including consideration of environmental aspects. It is far beyond the scope of this course, but there are methods like the shadow cost methods based on life cycle analysis that monitorize the environmental costs of not being sustainable. These costs have to be borne by society. In the third course, you've learned about indoor environmental quality, which is the primary reason to build houses and use energy systems. We want and need a safe and comfortable indoor with good thermal comfort, quality of air, but also proper lighting, view and acoustic. For a part, this is determined by building design. But for an even large part, it depends on proper HVAC design, like controlling temperature and humidity, making sure the air is clean, removing pollutants, bringing air, heat and cold where they are needed. And when it comes to HVAC systems, for sure, as we have seen in the present course, it is about air handling units and humid air, and pipes, ducts, zones and control. But it is more essentially about maintaining an excellent indoor air quality while helping to reduce the energy demand and the peak load and choosing or even designing the energy supply system. So in the end, HVAC designers and engineers have the exciting and demanding task to integrate all these aspects together into a HVAC system, guaranteeing a high indoor air quality and thermal comfort, guaranteeing a high energy efficiency because this is necessary for the utilization of renewable resources with low or no emissions and low or no resource depletion. And of course, it must be doable, therefore affordable in both terms of investment and operational costs, comprising of energy bills and maintenance. This is not work that you can do in your own, especially not in large buildings, so there is always intensive collaboration involved at all levels of a design project because you need the expertise of others. Of course, you are working together with the client and the architect, but the client may have many faces, building owner or building manager or facility manager, and not to forget the occupant. And of course, the architect and the other consultants and engineers like the structural and building physics engineers. By working together with them, specific creative solutions can be found, like combining ducts with load-bearing columns or ventilating through double-skin facades. In many cases, IEQ experts are needed, like in labs and hospitals, and sanitation engineering is not to be forgotten. Electrical and control engineering are of main importance. No HVAC work without it. With complex buildings and equipments, you will need simulation experts, not only about energy, but also about fluid dynamics and air distribution patterns. Close collaboration with energy companies will be needed, especially when it comes to connection with energy grids. For specific technologies like geothermal-based and solar, you'll need expert companies and you may need many different permits depending on technology and regulations. And discussing your designs with maintenance engineers, commissioners and building energy management experts who will play a main role during the operation of the HVAC system is a must. There are also specialists drawing all PNIDs, like in CAD, for instance. You may work with scientists on new developments, often that will be together with producers, think of heat pumps, PV cells, hydrogen technology, smart grids, and even high-efficiency valves and hydraulic components, heat exchangers, etc. And finally, don't forget the cost experts. Let's look now at the design process. Well, any design starts with a program of requirement. In the past, the usage was that the program of requirement was made by the client and the architect, telling the HVAC designer what he should use. Double glazing, for instance, and a heat pump, or a chiller from a certain brand. This is well possible when HVAC equipment is relatively simple, but in larger buildings, and when aiming at sustainability, it cannot be done like that. It is expert work. So more often nowadays, HVAC designers are asked to set up the program of requirement together with their client, or the client formulates much broader requirements, like about the room temperature range to be achieved, or the acceptable humidity and how many people will be in the building. He or she will be prescribing performances to be achieved rather than means how to achieve it. This is called performance-based requirements or contracting. After this phase comes the phase of basic design. In this phase, first ideas are developed and discussed with the client, the architect and other experts. Will the direction be more towards heat pumps or connection to district heating? Is it going to be a high-tech HVAC with lots of controls, or a less sophisticated but more robust one? Which insulation level will be chosen? What type of glazing is recommended? Which zones can we think of? Will the ducts be sized for all air or for hygienic air? What about solar panels, etc.? This phase is creative and interactive. Building simulation tools may be used and may result in a few different designs in which the wishes of architect and client are integrated into possible practical solutions. As for the budget, it is based on cost indicators from former projects. The final choice is made by the client or the architect. As third phase comes the preliminary design, in which the ideas developed in the basic design are worked out to first PNIDs describing how components will interact. Preliminary design values are chosen based on load calculations and estimation of annual energy. This is often based on simulation nowadays. Volume flow rates of air are estimated in order to size the ducts and look how to integrate them in the architectural design. Approximate size of technical rooms are calculated, decisions are made about zones and layout. Don't forget that at the same time the architect is developing the building design itself, by which a lot of tuning and alignment is needed. In this phase, electrical and control engineers also make a preliminary design. Finally, after a choice has been made, the fourth phase comes in which the complete design is worked out into the smallest details, involving the work of a large team. After that, there may be a tendering or awarding phase, and the constructor will start with building the building and its systems. HVAC engineers may then play again a role in supervising the HVAC construction and taking care that all delivery procedures and needed checks are done. Think of checks about compliance of insulation, boiler temperatures, heat and cold delivery in rooms, quality of ventilation, etc. This is a phase of tuning of the equipment. During the operation phase of the building, which covers a long period of many tens of years, HVAC engineers will take care of appropriate maintenance, data analysis from the building energy management system, and optimization of the operation. There are nowadays lots of developments in the automated continuous optimization of operation. Finally, a few words about some of the technical tasks that the HVAC designer will encounter. The order of the task does matter in this slide. During the design phase, even before thinking about the energy supply or the level of insulation, you will make estimates of the size and layout of ducts. This is because this is essential to the work of the architect. Then you will make heating and cooling load calculations with simple tools in the basic design and advanced ones in the later phases. This is the step where decisions are taken about insulation, for instance. After that, you will take some time to think really well about the energy supply and the generators with in the back of your head all performance indicators set by the client and by yourself. Maybe you have a vision about sustainability and energy efficiency. You will go further with thinking about zones and controllability of your design, estimate performances, and make cost estimations. This is an iterative process with lots of tuning with others, and this process is repeated up to the final design. If you specialize more into commissioning, your task may be to help developing the commissioning procedure. Commissioning is the process of making sure that all systems and components are correctly installed, tested, operated, and maintained. Finally, HVAC designers are more and more involved in the operational phase, where they make checks, analyze the data from the building energy management systems, and propose improvements. As said earlier, there are many developments in this area. In this lecture, we have seen that to design efficient HVAC systems, a good thermal design of the building is needed, as well as the right choices of energy generators and much attention to indoor environmental quality. The right ingredients are needed to design further and efficient HVAC systems. We also discussed briefly the performance indicators that can be used. And we also described how the design process works and what is involved with it. I hope you enjoyed it. Thank you very much for your attention.